Hello, this is Elif Öztürk. I'm gonna answer chapter 6 questions. I don't know why, but I can't reach my online access. That's why, firstly, I will read the questions from my book, and then I will answer with the sketch. Okay, let's start with the question 1. The question 1 says that how could you transformations be used to describe the butterfly shown in the picture? See the detective and place a picture of a butterfly in a new sketch. Apply transformation to this butterfly to determine whether the butterfly has any symmetry. Okay, let's open. I found a butterfly from the internet, and then it's as you see that let's actually this is a butterfly, but I can show that it can be the symmetry line, and let's do as a butterfly like this. Then nearly it seems to butterfly like, and mark as a mirror this one, and then select the items and then go to the reflect. Yes, as you see that it's a symmetry line, and I got the butterfly. Yay! There are 2 butterfly. Yes. What about this one? Just pick as a mirror and then pick just this one, which is I can't, and reflect. There's another butterfly as you see that, but the first one was better. Anyway, as the book shows that the butterfly has symmetry line which reflect the butterfly's wings. I tried to draw a butterfly with the sketch, and as you see that on my sketch, and there are 2 wings, and which are symmetry to each other. Question 2. Question 2 says that does the butterfly have reflective symmetry? Explain. Yes, the butterfly has a reflection symmetry. As you see that the symmetry line reflective the wings of butterfly. Question 3. Rather than considering a butterfly, we can consider a polygon. How many different lines of symmetry does a rectangular have? Describe them. Okay, let's draw a rectangular here. And I need to pick this one. It's not enough. Okay. It and pick this one. Forgot to make it. Okay, anyway, the perpendicular line. And then also I need a perpendicular line there. Yes, there's another perpendicular line, and just need it. Yes, I place this one on there. I'm gonna get a perpendicular line, then hide some of lines. Hide these objects. Okay. Do it again. Yes. It's a perpendicular. How can I understand it? Let's find the angle. Yes, that's a right angle. No, it's not. Why? I had to have if I draw there. No, it's better to pick this one, and then go to the parallel line. Yes. And then I'm gonna get the right angle. Yes, perfect. Right angle. It's right angle. And it's right angle. And let's write some of them to get rectangular. Now I get a rectangular. Yes, I can say that these diagonals are the symmetry, and symmetry, as you see that these lengths are the same and these triangles are the same, which is the two diagonals are the symmetry line. And also if I make it midpoint, where is midpoint? And then I need the midpoint of this one, and that's a midpoint, and find the perpendicular line. And also I need this one to find midpoint, and also pick this one and this one, and where is the perpendicular line? Yes, also this is a symmetry line too of this rectangular. As you see that it's a rectangular and it has just two different lines of symmetry. And question 4. Suppose that a student claims my rectangular has four different lines of symmetry, two lines through the middle of rectangular and two diagonal lines. Is the student's claim correct or incorrect? Describe how you would respond to the student. Yes, also the question 4 says that suppose that a student claims my rectangular has four different lines of symmetry, two lines through the middle of the rectangular and two diagonal lines. Is the student's claim correct or incorrect? Describe how you would respond to the student. Yes, the student is right, and I showed all the symmetry lines before the question 3, and there are two symmetry lines, which are two of them are diagonals. These are diagonals, and these are the middle of the rectangular. Question 5. What may be some advantages and disadvantages to using images of real-world objects to have students consider reflective symmetry? The advantages of teaching symmetry in schools looks beyond geometry forms to organic shapes, meaning animals, plants, every items, etc. Children have natural curiosity about the world around them, and learning about symmetry encourages the students' interest. It will help students learn well to the symmetry. If I mention about the disadvantages of using images of real-world objects, if the students don't understand well the symmetry the first time, when they see the object does not have a symmetry, they can be confused about the topic, and to teach them with every details may take a lot of time. Question 6. Find an image of a real-world object that would have more than one line of symmetry. Discuss how you would use the image with students. I think it can be the sphere, like one is sphere from the Google. Yes. Go to the sketch. Yes, as you see that if I use the center of the sphere, as you see that there are lots of, like, the infinite number of symmetry you will see. Question 6, I answered. Question 7. Question 7 says that create an equilateral triangle and select the equilateral triangle. Determine the number of different lines of symmetry for equilateral triangle. Explain. Yes. We call it IBC. Is an equilateral triangle, and it's there are, as you see that these are symmetry lines, which is just 3. There are just 3 symmetry lines. Question 8. Create and explore a square. How many different lines of symmetry does a square have? Let's go to the file and made a square. Let's make a square. Find the length before it, and then go to mark mirror and pick these are and reflect. Not reflect, rotate. As this, and then put a mark end of it, and then again mark it, rotate. Great. And the length of it, then yes, great. EF, we can call it, or anyway, and then mark this one, pick point and the line, and rotate. Yes. Let's find the length of them. Great. The third one also equals the other ones. The last one, all of them's length of the lines is 3.67 centimeters, and as you see, it's a square, and diagonals are the symmetry line of the square, and also I can say it. Find the midpoint. It's midpoint on a perpendicular line, and also line perpendicular. Yes, there are 4 symmetry lines for the square. 9. Question 9. Create and explore a regular pentagon. How many different lines of symmetry does a regular pentagon have? I think it's better to find a pentagon from the Pentagon. Google Pentagon. Yes, it's a pentagon. Let's carry this pentagon to there. And why I can't? Anyway, let's carry again or open a new sketch and then carry this one to the new sketch. Yes. And I think this is my first line symmetry. What about the other one? It can be I think it's better to use this pentagon. As you see that there are 1, 2, 3, 4 and 5 symmetry lines. Question 10. What do you notice about the lines of symmetry for regular polygons that I have an odd number of sides? How does this compare to the lines of symmetry for regular polygons that have an even number of sides? I have noticed that if the shape is a regular polygon, we should look the first time that the regular polygon has how many sides. It is independent that the regular polygon which is odd or even. Like if this shape has 7 sides, there will be 7 symmetry lines. If the shape is 4 sides, there will be just 4 symmetry lines. Question 11. How many different lines of symmetry does an n-sided regular polygon have? Explain how you develop the generalization. N-sided regular polygon has n different symmetry lines. I can make these generalizations because a square has 4, a pentagon has 5, and an hexagon has 6 different symmetry lines. That's why n-gon has n symmetry lines. Question 12. Consider the recycling symbol. Does it have rectangular symmetry? Explain. First of all, we need to find a recycling. There's a recycling shape. Yes. I consider the recycling symbol has 3 symmetry lines, which are, one of them can be this one, like almost, I can say this one. The other can be this one, the other one can be this one. These are approximately, I draw it, but there are 3 different symmetry lines. We can consider that it's an equilateral triangle. Question 13. Does the recycling symbol have rotational symmetry? Explain. I can say the recycling symbol have rotational symmetry because degrees is 60 degree that make it as a equilateral triangle. Question 14. What order of rotational symmetry does the recycling symbol have? In my opinion, if we turn the recycling symbol 120 degree counterclockwise, the recycling looks similar to the original picture. If we turn it another 127 degrees, the result will look just like the original. Question 16. Does the foil have any reflective symmetry? Explain. Where is the foil? Where can we find the foil? Anyway, you can search from the Google. Yes, and which one we should use it? I think that's a good shape for it. With my sketch. Open a new sketch and then which one is better here? I think this one is better. Create dash. Yes. Let's look at. I think this is one symmetry line. It is another one, and this is another one. What does? I think this one also the symmetry line. This one also, and this one is also. Yes. I can see more the symmetry lines. And we can see that there are 6 reflective symmetry lines. Question 17. Discuss any possible relationships between rotational and reflective symmetry. As we see that the rotational symmetry without reflection and rotation symmetry with reflection gives the same shapes. It doesn't matter for the regular shapes. And where can we find it? Like, I wanna show the example of it. Where is my answers? Yes, and copy paste. And these are the rotational symmetry without a reflection, which and this one also rotational symmetry with reflection. And this is totally this original shapes that gives, but that's the shapes. But sometimes they are gonna have the same size, but the way can be changed. Question 18. Question 18. Use the regular polygon custom tool to construct an equilateral triangle. Place a point D and the sketch that will be used as a center of rotation. Rotate the triangle about point D using an angle measure that you think will result in an imaged triangle that will coincide with the original triangle. If they do not coincide, coincide, the center of rotation may need to be moved or different angle is needed. Is there a point where there is more than one rotational symmetry? If so, how many or what angle measure was used for the rotation? Let's go to the my equilateral triangle. Where was it? It's not this. I drew it before, the equilateral triangle, which all the angles are 60 degrees. And as we see that in the sketch, when I rotate the triangle about the point D, which is this one, let's mark it as a point D. Yes, using the angle measure 120 degrees, it will give us the original shape. There are two more rotational symmetry when we rotate 120 degrees, which gives the original shapes again. Question 19. How many different rotational symmetries does a square have? How about a regular pentagon? Explain. A square has four rotational symmetry. Lines and rectangular rotational symmetry degree 90 degrees. For a pentagon, there are 5 symmetry lines and the rotational degree will be 72 degrees. Question 20. How many different rotational symmetry does a regular angon have? Explain how you develop these generalizations. If I have angon, that means I have n rotational symmetry, and if I rotate the angon 100 divided by n degrees, I'm going to have the same shape. If I rotate the shape n times with 100 AD by divided by n degrees, I will have totally the same shape. This is a generalization of rotational symmetry. Question 21. Describe a polygon that has A. Rotational and reflective symmetry, B. Rotational symmetry and no reflective symmetry, C. Reflective symmetry and no rotational symmetry. And this is for the example of A. Rotational symmetry without reflection. It's for B. Rotational symmetry with reflection. And the C is the C can be what does this one? This one shows that reflective symmetry, no rotational symmetry. As a first one of reflection symmetry, and there is no reflective symmetry. Isolates trapezoid, and the other one is irregular quadrilateral. And also there is no rotation symmetry for it. Question 22. A student notices that a center of rotation for a regular hexagon is located where the bisectors of the vertices of the hexagon intersect. A student asks why this happened. How do you respond? As the question says that when a student realizes that the center of rotation for a regular hexagon is located where the bisectors of the vertices of the hexagon. Okay, let's go to the Google and find an hexagon. Symmetry lines. I think it will be better to see that. Yes. If a student asks me why the reason, I would answer them Hexagons are the unique regular polygons such that the distance between the center and each vertex is equal to the length of each side, so the center must be the intersect of these 6 triangles. There are 6 triangles which are all of them are equilateral triangle. That's why it must be the bisectors of each vertices if we look for the symmetry line. Question 23. Locate other real-world applications to symmetry in the field of science. Describe the examples of explain how they might be used for teaching students about the symmetry. I found the example from the internet, these snow crystals. I would like to give an example in science, which is snow crystals that have symmetry. As you see that it's fabulous. Question 24. There's a schema which is I think it's better to look there. The question 4, describe other examples of regular tessellations. Regular tessellations means a tessellation made up of congruent regular polygons. Question 25. Open the sketch regular polygons GCP. Determine which of the following regular polygons will tessellate. That can be used to form a tessellation. You can use your DGE to apply transformation to the original regular polygon to determine whether it will tessellate. Consider the measure of the interior angle for each of the different regular polygons. Yes, as you see that the regular polygon are triangle, quadrilateral, pentagon, hexagon, heptagon, octagon, nonagon, and decagon. And measure of interior angle for triangle 60. The tessellation, yes, we can make a tessellation. What about the quadrilateral? Quadrilateral measure of interior angle can be the 90 degrees, and tessellation is can be used for it. The pentagon, the interior angle is 180, but we can't make a tessellation. And hexagon 120, and we can make a tessellation. The heptagon, this is 128. 4 divided by 7, it's an interior angle, but we can't make a tessellation. The octagon interior angle is 135, and we can't make a tessellation. The nonagon interior angle is 140, and as you see that we can't. The last one is the decagon. The interior angle is 144, and we can tessellate it. And as you see that there's empty. It doesn't connect these pentagon, octagon, nonagon, and decagon. Question 26. What do you notice about the measure of the interior angles of the regular polygons that tessellate? What do you notice about the measure of interior angles of the regular polygons that you do not tessellate? Do you think that there are other regular polygons that might tessellate? Explain. Since the regular polygon is tessellation, it must fill the plane at each vertex. The interior angle must be an exact divisor of 160 degrees. This works for a triangle, square, and hexagon. And you can show working tessellation for these figures. For all the others, the interior angles are not the exact divisors of 160 degrees. And that's why they can't tessellate. Question 27. Regular polygons cut from the cupboard and paper could also be used for complete table in question 25. Describe the differences of using cardboard polygons versus polygon constructed using LDGE. What effects might those differences have on what students learn about tessellation? In my opinion, regular polygons cut cupboard is easy to understand and then constructed using LDGE. Using DGE is more complex to draw with it. On the other hand, it's a fast way to draw all the tessellations in a short time by DGE. Question 28. Determine whether it's possible to tessellate the plane using two or more regular polygons. A regular tessellation is design covering the plane made using a type of regular polygons. A semi-regular tessellation is made using two or more types of regular polygons. With both regular and semi-regular tessellation is arrangements of polygons around every vertex point must be identical. I will show that on the by Google. Yes, as you see that we can use the different polygons at the same time. There is square and a hexagon. Question 29. In your DGE, construct a parallelogram and determine whether it will tessellate. Drag a vertex to determine whether other parallelograms will also tessellate. Create an argument to convince a friend that a parallelogram will always tessellate, or provide a counterexample. Okay, let's make a parallelogram. Click these two and find a parallel line. Yes, and this one. This one. Let's go to the parallel line. Yes, as you see that all these are. This is a parallelogram. Let's hide this. Let's make a certain firstly, and then hide these. Anyway, still it's a certain to make it parallel. Yes, this is a parallelogram. And what about the tessellation? I did translate. There's another one, and I need to carry it. Yes, it fits to each other. And then other one. Yay! The other one. Yes, it's tessellate. And I use the sketch and construct a tessellation with the parallelograms. The parallelograms will always tessellate. As you see that there can tessellate as an infinite number of parallelograms. Question 30. We saw earlier that a equilateral triangle will tessellate. Will any triangles tessellate? Explore using your DGE and provide an explanation or counter example. Where's my and this is my equilateral triangle, and let's hide them, these symmetry lines. Yes. What about tessellation? Yay! Yes. Excellent. And all these are 1, 2, 3, 4, 5, 6, 7. There are several equilateral triangles. That means I can tessellate all these triangles, all these equilateral triangles. But on the other hand, using irregular triangles, children will discover that all triangles and all equilateral triangles will tessellate. It's because the sum of the angles of quadrilaterals is 360 degrees. And the sum of the angles of the triangle is 180, which is the factor of 360. Shapes will tessellate if the sum of the angles around the common vertex equals 360, as illustrated below. And this one, yes. All these if I put it there, yes, and all interiors are 160 degrees, and this line must be 180, and this one must be 360 degrees, and that's why we can tessellate all the triangles. Question 21. Explain how the process you use to construct a shape starting from the parallelogram to tessellate ensures that the final polygons will tessellation to plane. First of all, we need a parallelogram. Let's use just one of it. Yes, and hide all these points. Great. And let's make a shape. As the book made like this. Great. And then let's make it tessellate this one. Yay! It fits there. Yes. And I also this one, make it like this. Other one. And let's tessellate this one to there. Not this one. I think it's better to put it like a small one. And then with it there. Yes. And hide the side of parallelogram. Excellent. And pick this one Let's see. Let's find it's tessellate or not. Yay! I connect perfectly. This one. And excellent. The other one is going to fit perfectly. Yes, excellent. And as you see that, I tessellate all of them by parallelogram. Question 32. Can any regular polygon be used as a starting polygon? Why or why not? No, it cannot use any regular polygon be used as starting polygon. Notagon cannot be used for tessellation, that's why any polygon cannot be used for tessellation. Question 33. What polygon do you think Escher started with when he created a tessellation shown in figure 6.5? I can't show the Escher tessellation there. I will just answer. I think square used when Escher starting to create the tessellation. Question 34, sorry. When, if ever, will you need to rotate or reflect the tilling polygon to successful tessellation plane? Let's find the tilling from there. Where's tilling? I wrote it wrong. Yes, tilling. And I think I need rotation while the tilling polygon to successfully tessellate the plane. Yes. Question 35. Can shapes other than polygons be created to tile? Yes. As you see that we can use other than the polygon be created as a tile, and also as you see that it's not a regular polygon, but we can tessellate. Question 36. Describe how the use of dynamic environment to create an Escher-like tessellation might be helpful or distracting to students. I think it's fun to make tessellation, and it helps students understand well all the tessellations, reflection, rotation. I don't think the distract the students. This is an example of the prices that's used for by tessellation. For example, let's go my answers. We can use in a real life these tessellations, and as you see that it's the oil prices graphics. The last question is examine the Common Core State Standards for Mathematics 2010 and determine where and if you might introduce students to tessellation. The Common Core says that for mathematics addressed by tessellation puzzles, the number of the specific standard follows the quoted standard in parentheses. Recognize and measure as additive. Identify the symmetry figure and draw lines of symmetry. Recognize a line of symmetry for a two-dimensional figure. Understand that a two-dimensional figure is congruent to another if the second can be obtained from the first by a sequence of rotations, reflection, and translation. I answered all the questions. Thank you for listening to me.